Hi, my name is Dan Dorsch. I'm this year's Graduate Drive It winner, and my invention is a clutchless hybrid transmission. And before I get into too much detail about that, I want to tell you about me and basically convince you that we're all the same as you guys, and you guys are going to go on to do awesome things over the next few years. So you can see here me playing with Legos at about age 7, and then again in high school. Our high school had a Lego robotics team, didn't have FIRST Robotics yet at that point. And kind of what I've realized, and even to this day still do, is Legos are a super good tool for getting experience with hands-on projects. I still use them to prototype different inventions today. Moving forward from that, I realized that every hobby you do, there's chances and opportunities to be inventive. Here I am in high school with RC airplanes and helicopters, and you're always trying to kind of adapt and adjust to come up with the best performing or the toughest device. Science Olympiad was really the first opportunity I had where there was kind of a given design challenge, and we had to invent solutions to these design challenges. So pictured here is what's called the Scrambler event, and the challenge there was to propel a car with a weight, so you can see the weight launcher here, and stop as close as possible to a wall without scrambling the egg on the front of the car. The other event here is a boom lever, basically a tower you load with weight, a lot of you are likely familiar with. And the Right Stuff event, basically a rubber band powered airplane. So sort of designing more for challenges that were already set in place. And also really impactful is kind of my first car. I've always loved racing in cars. This is a 1990 BMW that I worked on a lot when I was in high school. Picture of me and my brother there. And kind of when I got the opportunity to work on this hybrid transmission, I was super excited, and it's a really awesome project. So these are two prototypes here. Some of you saw the demonstration of the right device. And I'm going to try to explain. I know cars, a lot of people know about cars, but maybe don't know how they work. So I'll try to give you the 5-minute crash course for that so you can understand a little bit more about it. First, the benefits of an electric motor. Why would one want to add motors? So you see here an Audi and a smart car. And the Audi is much faster, as you would imagine. Still waiting for the car. There it is. And now a smart car versus a Ferrari, if you shift your perspective, you realize that, I won't spoil it, the smart car is actually faster off the line than the Ferrari. And this is due to the torque density of the electric motor. So for example, Tesla is much faster, 0 to 60 even, than a Ferrari, but can't go up to 200 miles an hour. So performance is one benefit for adding electric motors. The second reason a lot of car manufacturers are beginning to hybridize is due to CAFE or corporate average fuel economy requirements. So you can see a plot here of those requirements versus time for passenger cars and light trucks, and realize that we have a long way to go, and so there's a lot of incentives for car manufacturers to come up with improved hybrids and other technologies for transportation. So let me give you a summary of the current hybrids. First would be similar to the Toyota Prius, which is focused on efficiency. And these have been around for a while, a really clever mechanism that they use to get such high miles per gallon. The second type, million-dollar supercars, the Porsche 918 Spyder, is really designed with a focus on performance. So the electric motors added in this hybrid architecture are added for performance reasons, and the goal in my research is to take both performance and efficiency into consideration and to develop a new type of transmission. So let me explain a little bit more about what a transmission does. So if you have the engine and the wheels, it's basically what couples those two together and allows for changing the gear ratios as you're driving forwards. So you'll see more figures like this, but you'll have shafts and the gears are always meshed, and then the gear shift lever will actuate a synchronizer, and basically if it moves left or right will engage the gear, and so that's basically the speed you're driving at. There's a few different types of transmissions. Again, as I mentioned, the Toyota Prius, with a very clever planetary gearbox transmission. A typical automatic car that you would drive has a torque converter, which is basically a fluid coupling. You can imagine a couple fans, one blowing on the other, and that's what causes both the spin. It's fluid-filled as opposed to air in this case. But the highest performance cars shown here in a Lamborghini are typically double clutch transmissions, so similar in nature to a stick shift car, but all of the actuation is done automatically. So looking at this closer, the question is, why would we want to remove the clutch? This is a really awesome system, but there must be some reason why we want to get rid of it. And you'll notice it's pretty complex. You see two concentric shafts, as well as it's a double clutch with multiple plates, and it's also fluid-filled. So it's not as efficient as it could be, and with these high-performance cars, adds quite a bit of weight and size to the total car. So removing that would be a big benefit for these performance cars. Shown here is a figure of a typical transmission. So you'll notice the elements that I'll be removing are the clutch and the reverse gear, which will be done on electric power. But say you're driving in fourth gear, you'll notice the clutch is connecting the transmission engine together, and fourth gear is engaged. So to switch gears, we'll take our foot off the clutch, or step on the clutch, disengaging the engine and transmission, shift into third gear, which will change the speed of this shaft, and then as the clutch is re-engaged, it'll change the speed of the engine. So that's the functionality we need to replace with electric motors. So getting rid of clutch and reverse gear, adding a coupling to the engine, and then adding a couple electric motors to replace that functionality. So the motor on the top here is used to prevent the lag that you feel when you typically shift in a standard car. So when the driver takes his foot off the gas and steps on the clutch, if you're accelerating fast, you kind of lurch forward a little bit. So this motor is used to fill that lag. The second motor does the job of the clutch and basically adjusts the engine speed very quickly during the shift. And this is a simplified model from how the architecture I showed yesterday works, but basically to kind of explain how it works for people who aren't familiar with how transmissions behave. So there's several benefits, as I mentioned: maintaining performance of a traditional internal combustion engine car. People who buy these super expensive cars don't want to feel like they're driving an electric car and have their friend just go zooming past them in their traditional engine-only car. Again, the higher initial acceleration from the motor gives a strong benefit for these cars. We also will have better fuel economy, especially for city driving, as we can drive around on electric motor power as opposed to having a 600 horsepower engine when you're driving around the city at 10 miles an hour. Reducing the weight and size and cost compared to a traditional high-performance hybrid is also super beneficial, as these cars are trying to remove grams and will spend hundreds of thousands of dollars to remove like a few pounds. So if we can remove the clutch, that will save us quite a bit of weight in the overall systems. I want to acknowledge a lot of people, my lab mates, friends and family, my advisor for the research project, as well as a couple undergraduate students that have worked with me, and two class teams who are really also inventors in this technology. It's all these, everyone here, it's really difficult, as you can imagine, like most things that are made today are not just the work of a single or a few person, but large teams of people. And I think moving forward, society's problems will continue to be large, multidisciplinary teams of people solving problems. So I want to thank everyone on this slide and leave you guys with the last idea of following your dreams. So this is a makerspace in mechanical engineering that started and launched last May, and I realized the need for it my senior year at MIT, and it took about 3 years of hard work, people saying there's no way it could ever happen, students aren't responsible enough to build a makerspace, to manage a makerspace, and we finally got it open and have had over 600 people trained in the space and using it. So basically, even though we had a lot of hardship during the process, it's super awesome to see it actually working today. So thank you so much. Sure, and definitely feel free to reach out to me, anyone too, if you want to know more about it as well, because kind of part of the goal is to share and expand our knowledge. But for example, like EHS, environmental health and safety, just kind of students, especially undergrads, managing the space was at first a concern. It hadn't really happened here. Getting space at MIT is very difficult just because we're in such a tight campus. Many other barriers such as buy-in from faculty, staff, et cetera. So just kind of many steps to overcome that one wouldn't think of when starting the project.